Hello everyone. Today we are going to start with the fifth chapter, Oscillations. Now oscillation is a very common and interesting phenomenon in the world of physics. In our daily life we come across various examples of oscillatory motion. To name a few, it's like rocking of a cradle, swinging of a swing, motion of the pendulum of a clock, the vibrations of a guitar or violin string, the up and down motion of the needle of the swing machine, and so on. Now, here when we have to talk about oscillatory motion, we need to remember few points and let us discuss about these points. When we talk about oscillatory motion, it is a to and fro motion of a particle about mean position. Oscillatory motion is also called as a periodic motion as it repeats itself in definite time interval. When we have to study oscillatory motion, we need to have the basic ideas of certain terminologies used, such as time period of the motion and frequency and amplitude. Let us try to get one by one. When we talk about time period of the oscillatory motion, it is the smallest time after which the to and fro motion is repeated again and again. Now time period is usually denoted by capital T and its SI unit is second. The number of oscillations covered per unit time is called as frequency of the oscillatory motion. It is denoted by small n and its SI unit is hertz. Now depending on the path taken by the particle, the oscillatory motion can be distinguished as simple harmonic motion and angular simple harmonic motion. Now if the path taken by the particle is a straight line, it is called as linear simple harmonic or only simple harmonic motion. And if the path taken by the particle is an arc of a circle, it is called as angular simple harmonic motion. Now when we have to talk about the amplitude of the particle, amplitude is defined as the maximum distance covered by the particle on either side from the mean position. Now remember, amplitude is a vector quantity. Now as I said, we need to remember few points when we are discussing about oscillatory motion. The points are as follows. A complete oscillation is when the particle goes from one extreme position to the other and comes back to its initial position. The conditions that are required for simple harmonic motion are as follows. The oscillation of the particle should be about a fixed point. The net force or acceleration is always directed towards the fixed point. The particle comes back to the fixed point due to the restoring force. Now as we said, oscillatory motion is a periodic motion which repeats itself in regular time interval. In this particular chapter of oscillations, we are going to see the displacement, velocity and acceleration for the oscillatory motion and how these different terminologies, that is velocity, displacement and acceleration, can be represented by sine and cosine functions. Now sine and cosine functions are called as harmonic functions. So harmonic oscillation is that oscillation which can be expressed in terms of a single harmonic function, such as x is equal to a sin omega t or x is equal to a cos omega t. Now in these equations, x is nothing but the displacement shown by the particle and a is the amplitude of the particle. Now when we talk about non-harmonic oscillation, these are the oscillations in which we do not use, or these are the oscillations which cannot be expressed in terms of single harmonic function. Now let us try to get some idea about what simple harmonic motion means, or what is the actual meaning of linear simple harmonic motion. When we talk about linear simple harmonic motion, let us first try to get the definition of that. The linear periodic motion of a body or linear simple harmonic motion is defined as the motion in which force or acceleration is always directed towards the mean position and its magnitude is proportional to the displacement of the particle from mean position. This is the statement of linear simple harmonic motion. If you want to remember it in a mathematical form, it's very easy. We write mathematically as F is equal to minus kx, where k is a constant. This constant, it depends upon the elastic properties of this spring, and it is also known as force constant or spring constant. Now, the negative sign that appears here in the equation, it indicates that the force and the displacement are oppositely directed to each other. Let us try to get the idea of linear simple harmonic motion with these three diagrams. We will discuss these three diagrams one by one. Now what is done here in the diagram, just focus on the diagram 5.1b. Now here what we have done, we have placed a rectangular block on a smooth frictionless horizontal surface and attach one end of this spring to the rigid wall and the other end of this spring is attached to the block. Now if you pull the block whose mass is m towards the right and if you release it, what will happen? The block will begin its motion, that is to and fro motion, on either side of the equilibrium, and this motion of the block is shown in 5.1a and 5.1c. So 5.1b is the diagram which represents the equilibrium position of the block. Now if you just focus on the diagram B, then as I said, it shows the equilibrium position in which the spring exerts no force on the block. Now if the block is displaced towards right from the mean position or from the equilibrium position, what will happen? We are stretching the spring in the right direction, but the force or the block will be directed in the left direction. Okay. Now on account of the elastic properties of this spring, what will happen? The spring will try to regain back its original size and shape, and therefore it exerts a restoring force on the block, and this restoring force, which is denoted or which is indicated by this arrow, is exactly in the opposite direction, and this restoring force is responsible to bring it back to the original position. Okay, so here also the mathematical statement of linear simple harmonic motion, that is F is equal to minus kx, is verified. We can say that when we are stretching the block in this direction, that is in the right direction, the displacement x is in the right direction, but the internal restoring force is acting in the or along the left direction. So F is equal to minus kx is verified. Similarly, if you focus on 5.1c, if the spring is compressed, that is if we are going to exert a force in the left direction by the block M on this spring so that the spring is compressed. Now here the displacement of the block is in the left direction, but because of the internal restoring force, the spring will try to regain back to its original size or shape, and it will displace or it will make the block move in the right direction. So the direction of the displacement and the direction of the force applied by this spring, they are opposite to each other. So from all these three diagrams which we discussed just now, the definition of linear simple harmonic motion or the meaning of linear simple harmonic motion is very clear to us. Now once the meaning or definition of linear simple harmonic motion is clear to us, let us try to discuss about the differential equation of simple harmonic motion. Now before discussing the differential equation of simple harmonic motion, we need to know what actually means the differential equation. Now remember, differential equations are generic equations which will help us to study or analyze all the different types of simple harmonic motion. Now you all know that when we talk about the motion or when we talk about Newton's laws of motion, all three laws, they help us to understand and analyze the motion in a very what we can say, they help us to analyze the motion completely. So similarly, if we know the differential equation of simple harmonic motion, we will be able to analyze all different types of simple harmonic motions. So let us try to derive the differential equation for S.H.M. Now from the definition of linear simple harmonic motion, we are aware that mathematically we can write S.H.M as F is equal to minus kx, that is force and displacement. They are proportional to each other, but as the negative sign indicates over here, they are oppositely directed. Okay, this is according to the definition of linear simple harmonic motion. But from the Newton's second law, we are aware that force exerted is equal to the product of mass and acceleration. So if you compare these two equations, we can write ma is equal to minus kx. Okay, now here m is mass of the particle, a is the acceleration possessed by the particle performing the motion. Now we all know that acceleration is what? Acceleration is time rate of change of velocity. And when we talk about velocity, we know that velocity is time rate of change of displacement. So if we have to write acceleration in terms of displacement, how we can write? Acceleration is equal to dv upon dt, that is time rate of change of velocity. And if we write velocity in terms of displacement, it will be d by dt of dx upon dt, which means we can write acceleration is equal to d2x upon dt square. If we substitute the value of acceleration here in this equation, we can write m into d2x upon dt square is equal to minus k into x. Now if we divide both the sides, left hand and right hand side of the equation, by m, what we will get? M here will get cancelled. So we will have only d2x upon dt square is equal to minus k upon m into x. If we rearrange the terms, we can write the same equation as d2x upon dt square plus k upon m into x is equal to 0. Now here this k upon m, substitute the value for k upon m as omega square, where omega is the angular frequency. So if we substitute k upon m as omega square, we can write the equation as d2x upon dt square plus omega square x equal to 0, or we can write the same equation as d2x upon dt square minus omega square d2x upon dt square is equal to minus omega square x. So this particular equation d2x upon dt square plus omega square x equal to 0 is known as differential equation of simple harmonic motion. Now using this equation, we will be able to derive the equation for acceleration, velocity and displacement for a particle performing simple harmonic motion. We will try to derive it afterwards.